So we were talking last time about this construction of quasi-coherent sheaves on prods, and in particular, that if I take the ring S and think of it with shifted grading, and then construct the corresponding coherent sheaf on prods of S, this is called O of K. All right, and this is a line bundle under reasonable conditions. S is generated in degree 1. Okay, great. So when I write something as a proj, I'm not just telling you the scheme, I'm telling you the scheme with a choice of line bundle. And this isn't the only source of non-uniqueness in the way you write things as proj, but it's the really important one. So important, O of K is not intrinsic to the scheme X equals proj S. I can't just look at this scheme and somehow deduce what O of K is by its schematic properties. It really is a choice. All right, so in particular, there's one kind of manifest, non-uniqueness in how something is written as proj, which we talked about, which is I could take the graded ring S bullet, or I could look at S D bullet, and of course I want so this is only the things in degrees divisible by D. And since I want this to be generated in degree 1, I have to divide the degrees by D. All right, well, there's an obvious functor on modules that takes a module, only looks at a graded module, of course, only looks at the things that are divisible in degree D. And so I can take M, and then I can take M divided by D times D here. And you can check, right? So proj of this guy is equal to proj of this guy as a scheme. And the quasi-coherent sheaf associated to these two modules are isomorphic as quasi-coherent sheaves. I will leave that to you to prove, but you just look at every open set and you say, oh, if I have a section here, I can write that as a fraction where the guy in the bottom has degree divisible by D, so the guy in the top has degree divisible by D. And I'm using here that I'm generated in degree. I don't want to do it. I probably am not really using that, but it's useful to think about it that way. Okay, great. There are some shenanigans that can happen if you're not generated in degree. Let's just say that. Okay, but what happens if we shift grading? Well, if I shift the grading here by D, that corresponds to taking this guy and shifting its grading by 1. So what I call O of 1 in this way of writing something as a proj is O of D in this way of writing it as a proj. So this is far from the only source of non-uniqueness, but this is an important one. So I can take something and write it as a proj and get a different line bundle as O of 1 or O of D. Right. So I had wanted and didn't quite have time at the end of class to think a little more concretely about this line bundle. So let's think about P1 and think about OK and P1. So P1, of course, is built out of, I think of this, I'm drawing the C points of P1. They form a two-sphere. And I can think of this as two copies of A1 glued together over the complement of the origin. So they sort of exclude this guy and you get d of x0, exclude this guy and you get d of x1. And if I pull out these 2 points, right, if I ever look, oh, sorry, I should put d plus. D plus would be good. So if I pass to one of these open neighborhoods, I will trivialize this line bundle, right? That's how we proved that this was a line bundle, is we proved that on each of these open neighborhoods, it's trivial. And the way we would trivialize it, for example, on d of x plus, is to say, I have a section of this guy called x0 to the k. So it's a generator of, take sections on d plus of x0 over k. Right? This is a degree 0 element of, I'm looking here at S equals C x0, x1. And O of k, this is S with degree shifted by k twitting. So this is a degree 0 element of this graded module. And so it defines a section of O of k. Why did I say on here, k might be negative? Right? If k is negative, well, this isn't a section on all of P1, but is a perfectly well-defined section on this open set. So now I ask, how does this look on d plus of x1? So on d plus of x1, I also have a generator, but it's x1 to the k. So if I want to think about how does x0 to the k look when I use this to trivialize my line bundle, what do? Well, I put the ratio here, right? This is x0 divided by x1 to the k. This is a coordinate on d plus of x1. D plus of x1 is isomorphic to A1, in this case of C. And the isomorphism is, think of this guy as the coordinate on A1. So what I'm telling you is what this guy looks like on the other guy is, well, I multiply by this positive or negative power of the coordinate. So it vanishes to order k, or if k is negative, it has a pole of order minus k. So what's happening here? What's happening is by sort of doing this shift, and this is true more generally, but it's helpful to think about it in this case of P1, what I'm doing is I'm taking things that I can think of as functions on my affine patch, but I'm forcing them to have zeros or poles at the extra projective stuff I'm adding in, right? So I can think of P1 as kind of a projective closure of A1, and which line bundle I'm in. Well, it doesn't matter as long as I'm only looking at things happening on A1. But then when I put in that extra point, the K tells me what the behavior of my function at that extra point has to be. Yes. No, no. What I'm telling you is that this function is a generator times a function which is 0 at right. This is the affine parameter. So right, when I'm thinking about this in terms of the usual projective coordinates, right? This is the point where x0 is 0. This is 0, 1. This is the point where x1 is 0. This is 0, 1. Sorry, 1, 0. So what's happening here is away from this point, I can think about my point as x0, x1, 1, right? And use this as my affine coordinate. And the question is, what happens when this tends to 0? That's telling me about what happens here. Right. So what I'm doing is I'm starting by looking on this patch, and on this patch, I don't have any zeros or poles. So I'm trying to figure out what happens at infinity. And the way you always do that is you change coordinates so infinity becomes 0. Positive K means you have zeros, negative K means you have poles. Right? This function vanishes at this point if K is positive, and it has a pole at this point if K is negative. Yep, good to talk about. Okay. So why am I making this big deal about line bundles? Why do we care about line bundles? Well, we've already gotten one sort of hint here, right? Which is when we were talking about projective space, we had these annoying things, and I kept saying they're not functions, and they're even more not functions than the functions that aren't functions that we consider on affine schemes. And now we have an answer to what they are. They aren't functions, they're sections of line bundles. Yes.
Sorry, again.
Yeah.
That should be like the sections of that should be figuring what elements of this.
Yes.
And those all have one.
Yes. No, 1, 0. No, they don't. No, it doesn't. X0 has a 0 here, but it doesn't have a pole here. That's exactly the point. Right? If I look at this, right, if I have x0, right, when I look in the coordinate patch where x0 is a generator, I write this as 1 times x0, and I say, aha, no zeros or poles on that patch. If I look on the patch where x1 is a generator, I say, aha, it's x0 divided by x1 times x1, so it has a 0 when x0 over x1. So exactly the point is it doesn't behave like a rational function. A rational function has the same number of zeros and poles, whereas a rational section of O of K will have K more zeros than poles. Okay, we're getting to divisors eventually, but that's exactly the difference. That putting this K here gives you an imbalance between the number of zeros and poles. And for like actual, we're seeing that in one case here, where if I force there to be no zeros or poles at all but one point, well, then everything has to get pushed to the other point. And I have to get that number of zeros or that number of poles at the other point. But more generally, if I took some crazy rational function, where the numerator had degree 1 more than the denominator. Well, I would have a bunch of poles, I would have a bunch of zeros, but I would have 1 more zero than pole with everything commuted up to multiplicity. Yeah.
Like, oh.
If you, we'll get there in a moment. So, I mean, right, I told you if you write a scheme as proj of a ring, that it naturally picks up a line bundle. So I think one way to phrase your question is, how reversible is that process? If I have a scheme and a line bundle, does that give me a way to write that scheme as proj of a ring? And the answer is, well, with more hypotheses, yes. All right. Any questions? Yeah. We're getting there. I think there is an answer to your question, but that's not quite the right way to ask it. So let me do the next topic and it will be more natural. Okay. So the thing that line bundles tell us about, which is related to your question, is they tell us about maps of my scheme into Pn. And I might as well put Pnz here, but if I'm working over some field, it won't change anything to put Pn over that field. So if I have a map from X to Pn, well, on Pn, there's a line bundle O of 1. And when I pull back, I get some line bundle. So let me call this pi. Pi pull back of O of 1. And I get more data than that. So as Caleb was just mentioning, if I look at sections on Pn of Z of O of 1, what I get is free abelian group generated by x0 up through xn. We haven't actually proven this, but right, the way to think about this is proj of the adjoin x1 up through xn. And so certainly degree 1 things in here give me sections of this line bundle. Trust me when I tell you there aren't any others. I'm not actually using, thus far, I'm not using anything about there not being any other ones, but it's true that there aren't any. Okay. So when I do this pullback, I can pull back sections. So this induces a map from this free abelian group, some of the xi's, into the sections on X of L. Or put differently, right, each xi has to map to some section Si in here. So we can think of this as just, oh, I get an n+1 tuple S0 up through Sn of sections. All right, and I think the answer to the question you were trying to ask is this data classifies maps to Pn. And of course, remember, if I write something, if S is generated in degree 1, then I can look at the map from, well, either Z adjoin x0 up through xn to S that sends these guys to generators. Or maybe instead of Z, I could take some base field K. More often, I would be working with S being a K algebra for some field. And then the sort of relevant notion of generators would be a spanning set of degree 1. So if I looked at this in terms of the schemes, right, this would be telling me that proj of S is a closed subscheme of Cn. Right, so writing something as a proj, we didn't quite explicitly do it this way, but is roughly equivalent to realizing it as a subscheme of Pn. And so line bundles, well, they don't necessarily classify precisely ways of writing things as proj, because you have to also have these generators, but it gives you maps into projective space. If my X is locally Noetherian, I mean, there isn't a canonical choice of such a thing. You have to choose the line bundle. Okay. All right, so how do we reverse this construction? So what's the data that we need to put? We need to put in X a scheme, L a line bundle. So line bundle, as discussed, is just sort of the slightly more colloquial way of saying invertible sheaf. So locally free sheaf of rank 1. And S0 up through Sn in the sections of this line. And I should emphasize here, this is an n+1 tuple. It is ordered. And this is the sections on X of L. So I've mostly switched from the notation, right? This is the same thing as writing L of X, but it's more common to write this section notation. And what do we get? How do we get something interesting about this? So the key notion here is line sections of a line bundle. Well, they aren't defined as functions themselves, but the ratio between them is a rational function. So if I look at Si divided by Sj and following this usual notation from Bacchial, it's convenient to write that as Si over j. This is a rational function. And it's defined X minus V of Sj. So just as you can define the vanishing set of a function You can also define the vanishing set of a section of a line bundle, or actually more generally a locally free sheet. And you can actually define this as a sub-scheme. The sort of important thing is this is the set where if I look at the stalk, the image of Sj in the stalk, that's in the maximal ideal of that point times the stalk of P at that point. And I can think about the subscheme by thinking about the annihilator. Is that right? I can think about the annihilator of the line bundle mod, the subsheaf generated by this section. That's the kind of scheme theoretic way of thinking about this. But, the idea is just, I'm dividing by Sj, and that makes sense as long as this is not 0. And if you're worried about how do I think about this as a rational function, well, I choose any trivialization, and Si and Sj can be written as functions times a generator, and that ratio doesn't depend on the trivialization you choose. Right? So one way to say this is uniquely characterized by Sj is equal to, or sorry, Si is equal to Si over J times Sj. The unique function, rational function that satisfies this property. All right, so I can define a map of x minus v of Sj to an by sending where this an that I want to think about is spec of z adjoin xi over j, where I not equal to j, from 0 up through n. So this this is really, I want to think of this as d plus of xj inside Pn. But that's just a copy of the affine space with these coordinates. So how do I define a map from this affine scheme, or sorry, this scheme? I don't know yet whether it's affine, it actually might not be, to this affine scheme. Well, defining a map to an affine scheme means defining a map of rings the other way. It means telling you what every function on the affine scheme pulls back to. So what's the map? Well, I take x I over j, and I send it to the rational function, and it's actually a function on this open set, xi over j. So, right, I tell you what a point in projective space is by telling you what the ratio between any two coordinates is. And that ratio is the ratio between the values of these sections. Now, if you start thinking about what that really means for schemes, it starts to hurt your head a little bit. And then you say, oh, right, when I think about schemes, I just think about the rings and I don't worry about what's happening with points. So whatever the points of this guy are, I can define a map to an affine scheme by telling you this map of rings. And that map of rings is exactly what the coordinates would sort of tell you was the right thing to do. So you kind of think about the coordinates and then translate that into maps of rings, and then you don't have to worry about points anymore. Okay, great. So what does this give me if I stitch all of these together? Stitching, I get a map from X Well, I would love to say all of X, but I have no guarantee that every point in X lies in one of these open sets, right? I'm defining what the image is on this open set, and there might be something in X which is at the zero set of all of these sections. And if you're in the zero set of all of these sections, this construction doesn't tell you where to go. To Pn, and I should emphasize, since X is a completely arbitrary scheme, I don't know anything about it, I'm putting Pn of Z. Of course, if X were an A scheme for any algebra, I could put Pn of A here, right? Since I'm just telling you where the polynomial generators go, any base ring I have on this side, I could use as the base ring for this polynomial ring, which would mean looking at Pn over that base ring. But since everything is a Z algebra, I can just use Pn of Z. Okay. So I've basically proven theorem if S1 up through Sn have no common zeros, then there exists a unique map to Pn such that my line bundle L, I had to choose a line bundle at the start, is isomorphic to the pullback of O1. And SI is, I should write the sharp sign here, is the pullback of the section X. Yeah. All right, and there's a point here I haven't addressed. So I've fixed my S0 up to Xn. That's told me I get a unique map, and under that map, I can choose this isomorphism such that I get this pullback. So we're pretty close to the data of a map from X to Pn is exactly the same as this data. But there's one sort of sneaky redundancy in here, which is I had to choose this isomorphism. Right? So choosing this isomorphism means an invertible global function on X. Up to multiplication, and would say, and L and these S0 up through Sn are unique to multiplication by F, which is in, so global functions, I should use my section notation, global sections on X of invertible functions. So this is a times, not an X. So this is the sheaf of invertible functions, sheaf of units. Right? If I multiply all the S's by an invertible function, I won't change what the ratios are, and so I won't change what the map is. Mm-hmm. We can get interesting embeddings for various ends. Let me come back to that in a moment. All right, so yeah, sheaf of invertible functions. So this is O of x t u. This is just the units in O of x u. Okay. And that's a sheaf because checking whether something is a unit is a local property. Something in here is invertible if and only if it's invertible when you pull it back to every stalk. Okay, so right, it's tempting to think about this theorem as maps into projective space are the same thing as line bundles. And maybe that's a slogan you should remember, but the question pointed out that, well, it's a little bit more complicated than that. Because I have to choose these S zeros up through Sn. Okay, so, right, fancy terms. Well, right, I mean, there's nothing here about being an embedding, right? This is just that the map is defined. And of course, yeah. Well, I mean, you can still get different embeddings into PN for different choices, but whether this is an embedding is like actually kind of a complicated question. Okay, so, right. Often, especially over, well, let me now just sort of simplify and work over a field. There's nothing really special about working over field, but it just makes the terminology a little more easy. So if I have a line bundle L on X, and I'm interested in this question of how do I think about the different maps that come from this line bundle? Well, I look at this space of sections. And I can write this in a more coordinate-free way. So instead of thinking about Pn with specific variables on it, I can, for V a vector space, I can think about proj of the symmetric algebra of this vector space, right? So turning this into polynomials, and this is the symmetric algebra over the field K. V is a K vector space. So this is just a coordinate-free way of saying the polynomial ring. And this is usually called P of V dual. And why is that? It's because V is the space of linear functions on the vector space V dual, right? So the actual points of this proj I think of as lines in V dual. Okay, great. In this language, I can modify this theorem to say map from X to P of V dual is equivalent to choosing a linear map from V into this space of sections with no common zeros. All right, so we're getting into real classical algebraic geometry here. So everything has weird names that were chosen back in the 19th century. So the name for this map from V into sections of this line bundle is called a linear series. And I feel like there's some other slightly even weirder name for it. It's called a linear sequence. A linear system, that's right. So you'll hear this both called a linear system and a linear series. The common zeros, V of S0 up through Sn, or in this case, it would be, let's call this map B, V of B of the vector space V. This V is the vanishing locus. This V is the vector space. I'm sorry about the notational clash. This is called the base point locus. And of course, an element of it is called a base point. And so if this guy is empty, we say the system or the series is base point free. So you could state this theorem as saying a map to P of V dual is equivalent to a base point free linear system. There are all these other names, like if V is two-dimensional, it's called a pencil. I can't even remember what it's called if V is three-dimensional. But, because people thought about a bunch of this stuff in kind of classical algebraic geometry, they came up with all these funny words for things. Right. All right, so the sort of uniqueness that they were asking about is that you also have the freedom to choose what this vector space is, and you get different maps to projective space by picking different subspaces in here. Mm-hmm. So what I mean is for, from here, I can map into LP mod MPX mod LP, which is the residue field of the point P, right? So I have a linear map from V into this residue field. And at any given point P, either that map is 0 or that map is not 0. And so being base point free means there's no point where that map is 0. So this map being 0, that's another way to say what it means to be a base point, right? What it means to be in this common 0 locus. But someone on Zoom asked the question, so they'll have to say whether they were satisfied with the answer. Okay, so these notions have their various names attached to how this works. So for example, degenerate linear series. This means that the image is contained in a hyperplane. What does that mean here? It means that the map phi isn't injective. It means there's a linear relation between the s's, which is the linear relation that cuts out that hyperplane. So every element of the kernel of this map defines a hyperplane which the image is contained in. So non-degenerate means that that doesn't happen. So you'll hear these words referred to. So what are some other things we should discuss around this? So a rational map from X to Pn, so I should have written a dashed map here. So this is kind of easier to define than an actual map. I choose the same data, but with an important exception. So instead of these guys being sections, I choose S1 up through Sn to be rational sections. And they just have to not all be zero. That's sort of useful. So if when I look here, I just need one of these open sets to be non-empty. I can get that if any one of the SJs is not zero. I should probably be assuming here that X is integral. If I wanted to be more general, I would say something like not all zero at all associated points of O of X. All right, so this gives us, I'm almost out of time, so I'll try to finish up quickly, but this gives us sort of a new way of thinking about maps into projective space, a new way of kind of thinking about how we sort of find maps between schemes in general, especially because in practice, almost all schemes we want to think about are quasi-projective. So just as an example, sorry, I forgot to say, there was sort of a question about how to sort of deal with this non-uniqueness. So of course, there's one way to deal with this non-uniqueness, which is to assume that this map is an isomorphism. So if X is projective, then this space lambda will be finite dimensional, because push forward under a projective map preserves being a coherent sheaf. So I can just take V equals this section space. This is called the complete linear series. So this is kind of the best map that we can get, or complete linear system. I have no idea which of these I prefer. I will probably just randomly switch between them. I apologize about that. So this is kind of the best chance we have to get a map out of this line bundle, right? So this gives us a map from X into Cn, where n is the dimension of this guy. People often write L with bars around it for this system. And if I look at other V's, what I'm doing here is there's a rational map from Pn to Pn minus k. I'm doing this composition, which hopefully will get me a rational map if I'm non-degenerate, and will get me, in some cases, will get me an honest map. In some cases, will get me not an honest map. And I should mention, there's no guarantee that even the complete linear system gives you an honest map, right? This section space might be zero. So for example, on Pn, if I take sections of OK for k negative, then I just get 0. There's no maps attached to this guy. On the other hand, if k is positive, then I do get a perfectly good map. If k is positive, I get what's called the Veronese embedding. Or the k-upal embedding. So this is the map that sends your projective coordinates to all degree k monomials in those projective coordinates. So for example, for B1, I take x0 and x1, and I send that to x0 to the k, x0 to the k minus 1, x1, etc. There's another important map called the Segre embedding, which embeds the product of two projective spaces inside the n plus 1 times n plus 1 minus 1. And where this comes from is there's a line bundle, which is O of 1 on this Pn. I do what's called outer tensor product with O of 1 on this Pn. And this is called O of 1 comma 1. So this is, I take the pullback of O of 1 from here and the pullback of O of 1 from here, and I tensor them together. And the sections of this on the product are Cm tensor Cn. So again, you can write down explicit formulas here. It's basically the homogeneous coordinates here are all the pairwise products of homogeneous coordinates on here. And that's just sort of saying, oh, I have a basis of this tensor product that comes from taking the tensors of all the different pairs of basis elements in Cm and Cn. So yeah, I'm definitely out of time. So we'll talk about this more next time. Segre. So, before one thought about just kind of abstract proj, this was useful as the proof that the fiber product to projective varieties is projective. Yeah. Oh, let me just say, so I want to be careful here. The line bundle might not be defined on all of X. But I mean, the point here is like, what's a rational map from X to here? It's a honest map from an open subset of X into Pn, right? So how do I define a map on that open subset? Well, I have a line bundle on that open subset, and I have sections of the line bundle on that open subset that don't have any common zeros on that open subset. So, I'm choosing these rational sections. And if they have a common zero, well, as long as they're not all 0, that's going to be a proper closed subset, and I can remove that. And I was saying this thing about, oh, well, if you have multiple components, I have to make sure they're not all 0 at an associated point. Yeah. But let me not kind of carefully state that as a theorem. I think it's left as an exercise in Vakil to get the statement right. All right. I'm leaving it as an exercise. As I say, the thing I'm concerned about is like the line bundle might not be defined on all of X. I would be a tiny bit careful about that point. But the important point is if I do have a line bundle on all of X and I have rational sections that aren't all zero, those define a rational mapped projective space.